Chapter 16. So in chapter 15, we looked at, well, let me start by saying that when we're trying to gain information and determine a structure for a given compound, we don't get all the information we need from just one technique. I mean, it's better than it used to be, and we talked about that last week with the synthetic pathways that lead to a certain type of compound, and that's the way you verified that you synthesized the compound you think you have, or you isolated the compound that you think you have by synthesizing it. But now we get information. Last week we got it from mass spectrometry. And now we're going to look at infrared spectroscopy. And this was probably infrared, first infrared and then ultraviolet visible spectroscopy. Both of these techniques actually use parts of the visible and infrared spectrum to give us information. There's the outlet. And you probably have this in general chemistry already. This concept of wavelength versus frequency.
Yeah, I think I remember it.
Yeah, wavelength and the units of measure are in the meters. Now that's the international standard is in meters, and frequency, this Greek letter nu. The frequency is in reciprocal seconds, or actually hertz, which is the same thing. It's a cycles per second. In other words, if your eyeball is focused on just one place, how many of these waves pass that point in 1 second? That's the idea. So if you're going to do any calculations, hertz might not be the one you want to use. Well, reciprocal seconds, because number of waves is not a unit of measure. So that's why you only have inverse of seconds. And then the other important value is speed of light. And the 8 meters per second. And with those three, we can describe what light as a wave. So our formula then is C equals lambda nu. So if you check out your units of measure, this is in meters, this is in reciprocal seconds, so this has to be in meters per second. That's the way I look at it. What you'll notice is that light is taken as a constant. In the vacuum, this is in vacuum speed, but it works really well for air. So if this is a constant and these are variables, remember, anytime you have a product of two variables equal to a constant, you have an inverse relationship. That just means that if one of them goes up, the other one has to go down in order to maintain that constant. Okay. All right.
Now, would this stuff be in physics too?
Yep.
I thought so.
Mm-hmm. Yeah, you get it in multiple locations.
Yeah.
All right. Now, when Max Planck came along, he proposed and proved that and this had to do with the argument of whether light was a wave versus a particle. And there was a big row going on for most of the latter 19th and 20th century about whether light was this way or that way. And what we decided was it's both. I think Einstein had something to do with that. Anyway, if we take light as a particle, we call that particle a photon. And photon is the smallest part of a light beam that carries its fundamental energy. And this is where Planck came in and said the energy of a photon is equal to some constant, obviously Planck's constant, times its frequency. Now, I don't have the Planck's constant memorized, so there it is on the slide. And this constant is set up so that I'll just use the units of measure. It's joules seconds. So if this frequency is reciprocal seconds, then the seconds cancel and you're left with joules. So the energy is correct in terms of joules. That's the standard unit of measure. And as the frequency increases, so does the energy. We can look at it this way, or we can look at it, we can put the constant over here and then put energy divided by frequency. In this case, when you have a constant and a quotient of two variables equals a constant, then they're directly proportional. So we can calculate the energy of a photon of light, and the photon of light is related to the frequency. And since as the frequency goes up, the wavelength goes down, then as the frequency goes up, you get an increase in energy. But as the wavelength goes down, you get an increase in energy. So if the wavelength gets longer, you're decreasing the energy of your photon. All right, that was sort of a review, I guess. All right, and here's another representation of the electromagnetic spectrum. And it goes, in this representation, we have gamma rays on the left. So the shortest wavelength is on the left. The longest wavelength is on the right. And the energy increases from right to left. As the frequency increases and the wavelength decreases, we get an increase in energy. Where gamma rays are the most energetic photons in the universe. And I mean, we can simulate them here on Earth, but natural phenomenon, these gamma ray bursts that we see out the heavens usually come from very energetic activities like, I don't know, supernovas, black holes, merging black holes or neutron stars. You get these very energetic. Now I'm not sure. I saw somewhere, and I don't think it's in here, so I'm going to mention it now. If we've got gamma rays here, let's see, gamma. That's gamma. And then we have X-rays. Then we have ultraviolet. And we have visible range. Then we have infrared that we've looked at already. Then we have microwaves. And then we have radio waves. The what infrared information gives us and its interaction with matter has to do with energy that's put into the bonds of a molecule. So you get stretches. Spell that right. Stretches. And you get what is it when something flops back and forth? I hate it when that happens. Just had a chapter on it. I can't even remember. That's aromaticity. I want infrared. Wait a minute. That's what we're talking about today. Okay, so we'll get to it. And the less energetic ones are produced by other types of molecular atomic activities. But when we're moving this way, we're getting higher energy. Now we're talking about, with the visible and ultraviolet, we're talking about electron movements between orbitals. Actually, we can include all these. X-rays will come from that, but gamma rays come from nuclear activity. So you got something going on in the nucleus that produces the gamma rays. All right. The visible range is taken as, we used to always say between 400 and 700 nanometers because it was easier. Now remember what a nanometer is 10 to the minus 9 meters. And if you're ever going to use that formula, speed of light equals wavelength times frequency, you have to convert to meters. If it's given in nanometers, got to convert. Otherwise, you won't get the right, the units won't match up. But nanometers is more convenient. So we say 400, we used to say 400 nanometers to 700 nanometers was visible. But this author goes from 380 to 740. And that's probably accurate. And then wavelength. Wavelengths below this get you into the ultraviolet range. Wavelengths above that get you into the infrared. And we're going to talk about the difference in the way we measure things too. Because, yeah, infrared gets kind of wonky. All right. So this is a diagram, a picture of what an infrared spectrometer would look like. And what we have to do in order to get a spectrum, now you can do it in a number of different ways. There are spectrometers that will that are set up with multiple detectors. And if they're close enough together and you have enough of them, you can get a complete spectrum in one shot. Otherwise, you've got to take that mirror, let's see, fixed movable mirror, and you got to move it. In this case, they're moving it in and out to change the path length. And that scans through the wavelengths. You can also have movable mirrors that rotate like this. And the mirror itself can be a grating, like a prism. Grating and prism do the same thing. They split light into its component wavelengths. But if you've only got one detector, then you've got to scan. And the detector is calibrated so that when you're in a position here, it knows you're at this wavelength here, and it changes like that. They use what's called a stepper motor. So all you have to do is input a certain current or voltage, and it moves the motor a certain amount. It's calibrated to move it that way. But in this case, we have a single detector, and we're shining the light through the sample at a given wavelength. And what you're measuring is the amount of transmittance. So the system is calibrated so that you know the intensity of the source. You know how much energy is impinging on the sample from one side, then you measure how much comes out the other side. And that gives you the amount of absorbance. So then you're going to get, compare this intensity of the source, compare that to the intensity of the, at the detector. Okay. And then if you take the ratio of those, multiply by 100, then you get a percent transmittance. That is how much light is transmitted through the sample. You detected this much, you started with this much, so it's a percent that makes it through the sample. Okay. The problem with this measurement is it's not linear. It has a logarithmic curve. So what we've done is we take this value and let's see, there might be a slide on this one. We'll steal my own thunder. Well, actually, I stand corrected. I'm thinking ahead. For infrared spectra, we don't care if it's linear or not. We just want to measure the percent transmittance. So for now, that's good enough. So the percent transmittance would be at the top and the bottom would be 0. So our scale is 0 to 100% transmittance. So that's why in an infrared spectrum, you see the baseline is at the top because it would represent a 100% transmittance and there's no light at that wavelength being absorbed by the sample. Okay. So that's why the IR spectra are look like they're inverted. Your peak is coming along, it's going like that. I always thought that was strange. But when we break it down into why it's there, then okay. That's on the y-axis. Now on the x-axis, for some reason, organic chemists decided that they didn't want to use wavelengths. So they invented this thing called the wave number. And the wave number is simply the reciprocal of the wavelength. So if you take 1 over the wavelength, this is in centimeters. Okay, so it's reciprocal centimeters. This is the wavelength in reciprocal centimeters. That's called the wave number. Now, if you get used to using them, and they're all big numbers, right? I think the reason for that is the wavelength would be a negative power of 10, right? So let's just check one of them out. Let's say we're at 3,000, like close to where that big peak is. 3,000 reciprocal centimeters. Reciprocal centimeters. So let's invert that, and that'll bring it back to centimeters. Okay, take the inverse, and that gives us, how does it do this? You have to change the display. There. That gives us 3.33 times 10 to the -4th centimeters. And a centimeter is 10 to the -2 meters, right? It's 100th of a meter. So it's 3.33 times 10 to the -6 meters would be the wavelength in our standard measures. So that's why they're using this, because this gives us all whole numbers. So they go to centimeters. If we tried to use meters and did that, yeah, we'd end up with 30. Add 2 more. 300,000. Right, and that'd be a little big for our measurement. So it's a practical matter.
So in infrared, so is the stronger, like the larger the number, the stronger it is? Or is it the opposite? I think that's on the next.
Oh, you're talking about the energy?
Yeah. Well, I was just thinking because like red light therapy, that's infrared, correct?
Red light therapy, it's close,
Okay.
near infrared.
Okay, that's what I was thinking. It was that because I get confused between red light therapy and like we use laser therapy in hygiene.
Yeah.
And you know that it like attacks dark matter and can like hurt your eyes. So like I always wonder what the difference was between red light therapy and laser with that, because you would think that red light therapy would also harm your eyes. And it's just like a curing light in dental. It'll hurt your eyes too.
Yeah, they use UV light.
Yeah.
In curing for dental, that serves as an activator, because the resin that's been positioned wherever it is, the glue, for instance, when you're putting a crown in, they hit it with ultraviolet light because that we'll talk about that when we get to polymers, that initiates the reaction.
Yeah.
You have to have an initiator. And in that case, it's probably a free radical.
So why does it hurt her eyes? Because I was
Oh.
curing a sealant one time and I looked at that light a little too long and I couldn't see anything there for a second.
Yeah. It's ultraviolet light. It's like
Yeah.
looking at the sun.
Yeah, I couldn't
Yeah.
see there for a minute.
Red light therapy is probably not as dangerous because now we're talking about infrared light, which simply causes the molecules to either do this or this or that.
See, that's what I don't understand. How does it prevent or help with inflammation?
Red light therapy?
Because that's supposed to what it's supposed to be for, is to help with inflammation.
That's a physiological response.
Yeah.
Yeah. On the chemical and physical level, I can get an idea of what the red light's doing, but as far as benefits for inflammation, inflammatory response, that's physiology, and I'm not sure what the connection is there. So let's see, get back to your question. As the wave number increases, so if we're taking the reciprocal, and we know that as the wavelength decreases, what happens to the wave number? If this decreases, the wave number gets bigger. So as the wavelength gets smaller, wave number gets bigger, and that means that the larger the wave number, the higher the energy. So in this case, the energy increases from right to left. Okay, so these are known as, some of them actually produce peaks. Like that shaded one on the right looks more like a peak. It's just a single, but very often with infrared spectra, you'll see bands. They'll be wide. Some of them are very smooth. Like we'll see examples of those. So this is all based upon percent transmittance. The less light transmitted, the more light absorbed. That means, and what you've got is, depending on what the wavelength of the light and the parts of the atoms and molecules that it interacts with, light is only absorbed when we reach a resonant frequency. That is the frequency that allows a certain process to happen. It's like you got your niece in a swing and you're giving them a swing. If you push at the wrong time, you're going to stop them, right? And that's what you do sometimes. It's time to get out of the swing and go home now, right? So you push opposite to the swing, it stops them. But if you want to go higher, you push, and then when they come back just the right point, you push again. That's resonant with their period of motion. And that's the way light works. These molecules absorb light where you have a resonant frequency, a certain, let's say for a stretch, if you have a carbon and a hydrogen here, and their natural frequency is a certain value, a certain wave number, and they go like this, and then you shine light on them at that frequency, it makes them even more active. And they've taken up the energy from the light at that wavelength. And you see it as an absorbance. All right. Okay. A strong absorption is one whose percent transmittance is near zero. Right. So we know that the taller the peak from the top to the bottom, the stronger the absorption. And the weaker ones, of course, are closer to the top. Now, weak ones can give us information. But their differences have there are physical reasons for these differences in absorption. I should use the word absorption. because absorbance has a special meaning. We'll get to that in ultraviolet visible, where instead of transmittance, we use absorption. And we've done that in class, haven't we? Did we do the kinetics experiment? Yeah. Yeah, we use absorbance units. Right, so you've been introduced to that already. Okay, bending. Why couldn't I think of that word? So we have two types of motion that respond to infrared radiation. One is stretching. So the bond itself stretches. Now, it may not stretch much, but it stretches enough to for each particular type of bond, it stretches enough to absorb at a particular wavelength or in a band, depending on its neighbors too, depending on the environment. You may get a sharp peak, or you may get a broad band, or sometimes you get split peaks, right, for various reasons, and that gives you information about the structure of the molecule. Right? You can determine, in fact, early on in first semester chemistry, we learned that when a bench chemist goes in and analyzes a compound, they come out with percent by mass of each of the elements. That's it. And then we learned how to determine the empirical formula, how to use that to give us the molecular formula. And then you take the molecular formula and say, all right, now what's the structure? And that's what we're starting to get into now. This information on an organic level gives us the structure. So the distance between the two atoms is changing, gets longer and shorter. You have two types of stretching. One is symmetrical, and the other, well, the first one we talk about is the stretch of a single bond. But you can get two of the same type of bonds. For instance, we have this formaldehyde in the middle plate in B. That's formaldehyde, right? Those two hydrogens are bound to the carbon by the same bond, the same type of bond. So they can either stretch together, or they can asymmetrically stretch like this. One gets longer and the other one gets shorter. And that happens at a different wavelength. And then you can also get bending, where they go like that. Right? And when those hydrogen, actually they're protons, when those protons get close, they resist and they fly back this way. And then they come up here and they start to interact with the other parts of the molecule, and then they come back. So and that's symmetrical bending. You can also get asymmetrical bending, where the angle changes, the angle of the bond changes. I think it's on the next slide. There's asymmetric stretching. And there's, I guess they call it out of plane bending. Yeah. That's probably more important than the type of bending I was talking about. All right. Why does this happen? Well, this is a diagram of trying to explain what I put in words a little earlier. For each type of vibration, there's a certain amount of energy that's allowed. That's the resonant energy. That corresponds to the type of movement that is allowed in the molecule. And we think of it as two atoms on a spring. That's a good way to look at it. All right, so if we look at this on an energy chart, then you can see that the lower energy photon gives you a certain, you input a certain amount of energy, and it jumps up to a higher energy level, and you get more amplitude in the stretch. You can even excite it to the next level, right? So only IR photons of certain frequencies are absorbed by the molecules, and it's based upon what are they causing to happen in the molecule. So if you don't have a certain type of stretch, certain type of atoms that are stretching, or bending or doing whatever, then the molecule will not absorb in that frequency and on that wave number. And for that part of the spectrum, there won't be a peak. There won't be a broad or narrow peak at that point. So the infrared spectrum helps you find points of absorption, points of transmittance or light absorption, but it also shows you where it's not happening. So by process of elimination, you can remove certain types of bonds that are not there. Okay. So here we're pointing to exact values. The one on the left, 2961 and 1717 on the other one. So these wave numbers are pointing to particular frequencies that are being stimulated by the infrared radiation. That's why they occur. So here we are, let's see, are we comparing a couple of different molecules? Yeah. So for the purpose of comparison, we have the molecule on the top is a ketone. And the molecule on the left is an aldehyde. But the bond that's being stretched is a carbon-oxygen bond. So they're going to have stretch frequencies very close to one another. They won't be exact because they're in different environments, but they'll be close. And in that region around 1717 and for the bottom one, 1723, you know you have a carbonyl stretch right there. So the point of this slide is that frequency of a particular type of vibration doesn't change dramatically from one molecule to the other. It does change, but not dramatically. So this is where the art comes in. Experience and art. If you do this a lot, and that's not me. I did this as a student. That's the last time I did it. Well, and then of course the last time I taught this course, we got into it, but I don't use it on a day-to-day basis. So it fades over time. So this is one of those tables that I put in the handouts. Should have a copy of this table, all the tables that are in chapter 16 and 17, actually, you should have in that document. And this gives you the frequency range for each of the types of bonds and what they're doing and what the peak looks like, right? For an OH stretch in an alcohol or a phenol or a carboxylic acid. Well, carboxylic acid is going to be a slightly different range, but the alcohols and phenols are between 3200 and 3600 wave number. And it's going to be a broad peak, but very strong. So it's a very strong absorber of energy. Carboxylic acid is shifted somewhat, probably because it has that carbonyl group next to it. Right? You've still got the OH stretch here, but you've also got the influence of that carbonyl next to it that modifies its position. Amines have their amines are certain, like if you simply have an NH for your amine, but if you have an amide, that influences it also with that carbonyl. And then you have different CH stretches. There's a range for the alkanes, for the alkenes, for the alkynes. And these are still sigma stretches. So when they say alkanes, you've got something like that. But if it's an alkene, then you're going to have this. This carbon is attached to that double bond, and it changes the value. Or if it's an alkyne, then it's going to change it again. And then if you have an aldehyde next to it, if you have this, that's going to influence it. Then you have various others, nitriles, CNs. Now, we're going to talk about why these things happen in just a second. You'll notice that we've got the various differences here are of one, polarity, right? OH is definitely a polar bond because we get hydrogen bonding out of that one. Nitrogen, similarly, it's not quite as polar, but it's polar. Carbon hydrogens is relatively nonpolar. Carbon nitrogen triple bond would be polar. Carbon triple bond is nonpolar. Carbon oxygen is polar. Right, so you get the differences in polarity of the bond. You get the differences in the atoms on each side of the bond, based on mass. Like, excuse me, like oxygen is heavier than nitrogen. So we're going to talk about that in just a minute in reference to Hooke's law, right? Have you had physics?
No, I'm taking it next semester.
Taking next semester, okay. Hooke's law refers to the way springs behave. Right? It's more than that, but the basics of a Hooke's law is if you have a spring and you put a 1 pound weight on it, it'll stretch to a certain distance. And within limits, if you put 2 pounds on it, it'll stretch twice as far. So there's the relationship between the mass placed on it and how far it stretches. And you can also look at that in terms of how massive are the atoms on the spring, the bond. Right? The more massive, probably the slower it's going to vibrate. It's going to move more mass. Let's see, 6. Okay, we get bending modes. Okay, now we got bending modes. Number of bands. So the bending mode might have 2 bands. One at 910 and one at 990. And that would be for a I don't know what you call it, a vinyl. That would be a vinyl carbon strip bending. So we could run through those, but you got the table, so you can use it. You get, in fact, you get differences in monosubstituted aromatics, orthoposition, metaposition, paraposition, how that affects the bending. And these occur at shorter wave numbers, lower energies, probably because the aromatics are more stable. Okay, so let's see, what are we going to do with this one? Get that out of my way, I can't see it. I'll read it from the screen. Table 16.1 to estimate the frequencies where IR spectra would be for each stretching. So we would go after these particular, and we look at our chart and find the values. How does the frequency for particular IR peak relate to the molecule's vibrations? Right. Generally, the frequency at which an IR peak appears is the same as the frequency of the vibration responsible for that peak. Oh, we already know that. Okay. Alkenes are in the 1620 to 1680. So if we went back up here, we'd have an alkene here. We would have a stretch there. A CH alkene would be 3000 to 3100. So a CH, this one, the B, would be at 3000, 3100. And the ester is C, right? So that's ester because this carbonyl is attached to another oxygen that has an R group on it. So that's an ester carbonyl. It's at a certain wavelength. The CO in that ester is a different value, and the alkane, the pure alkane would be out here, this E. It's far enough removed that it's going to give us an alkane CH stretch. So that's what you would look for. If you actually had the molecule at hand, then you could look at a trace of it and pick out the peaks. But if we have a spectrum and we're trying to deduce the structure, it's a little more difficult. But these are the regions. The Q is a heavy atom, such as carbon, nitrogen, or oxygen, as usually compared to the hydrogen. So the QH single bond stretching is going to occur at wavelengths greater than 2500. So Q could be oxygen for an alcohol group. So the OH stretch would be in a certain region. I think it's around 3000. You got triple bonds, either carbon-carbon or carbon-nitrogen, and they occur between 2500 and 2000. So this particular spectrum has a huge peak there. So we probably have a triple bond. Double bond stretching occurs between 2000 and 1500. When you get below 1500, actually 1400 or lower, this is called the fingerprint region. And it's usually very, very complex. So we go to it last and use the information from the fingerprint region as a tiebreaker, or a way of eliminating certain types of geometry. And these include both stretching, single bond stretching, and bending modes. So that's probably why it's so complex, because it has a mishmash of both. Whereas out on the higher wave numbers, those are all stretches. All right. So this is just a collection. Heavy atom versus hydrogen stretch. Okay. I'm just trying to say the alkanes have sp3 hybridization. So what does that mean for the bond? Well, it means that the bond of a hydrogen attached to an sp3 carbon is going to be a sigma only. But remember what we said about electronegativities, right? The intrinsic electronegativity of this one is it's greater than this one and less than this one. So electronegativity would draw density away from a hydrogen bond. And so it should draw more energy away from this one. So what they're saying is if this is sp hybridized versus sp2 versus sp3, I'm trying to make sense of what they're saying here. We know that as the values get bigger, the energy of the photon increases, right? So it takes more energy to cause this vibration. It vibrates at a higher frequency. Maybe the electronegativity is the wrong approach. A better approach would be, no, electronegativity might work, right? Because the alkyne requires more energy. So the energy of the photon energy is increasing this direction. That means with a higher electronegativity, we're shrinking the bond. Does it take more energy to stretch it? That's what it's saying. I mean, the evidence is telling us that it takes more energy to stretch this bond than it does these. Its resonant frequency is much higher, its resonance energy is greater for the alkyne. Maybe just memorize it. Okay, so if we use this ball and string model or ball and spring model, as the masses of A and B increase, so we're not trying to claim one type of element or another on this one. We're just saying as the mass decreases from A to B. Okay. All right, going from A to B, we're decreasing the mass. So notice the bottom ball is shrinking to the green ball. So as that mass decreases, what happens to the frequency? It looks like the frequency increases. We're increasing the frequency as we decrease the mass of only one side. And as we stiffen the spring, then we also decrease the frequency. Okay. What does that mean for our spectrum, though? We decrease the frequency, that means we're going to higher wave numbers because that's an increase in, no, decrease the frequency, we're decreasing the energy, right? No, the frequency is increasing. I'm sorry. Frequency is increasing from top to bottom. So the frequency is increasing, the amount of energy is increasing, the wave number is increasing from top to bottom. Yeah. So that occurs with both decrease in mass of the atom and increasing strength of the bond. All right, so deuterium as an isotope of hydrogen has roughly twice the mass of hydrogen, but the two have nearly identical chemical properties. So if we compare a CH bond as essentially the same strength as a C deuterium bond, which vibrational mode for a stretch will absorb at a higher frequency in the IR region. So we've increased the mass, we should decrease the energy, correct? So CH should be a higher frequency. Okay. The spring stiffness is the same because the bond strength is the same. And so that doesn't enter in. We're focused on the mass only. Since deuterium is heavier than hydrogen, the vibration has a substantially lower frequency than carbon hydrogen. Yeah, it's a lower frequency for deuterium. Yeah. So it should absorb a lower frequency or a smaller wave number. Correct? Yeah, lower frequency is smaller wave number. Okay, here we're introducing Hooke's law. This is a little more involved than the Hooke's law that I got in physics. I mean, it was just simply right the distance that the spring will move has Hooke's constant, and then the times the mass. So as the mass goes up, the distance the spring moves goes up. But now we're getting a more detailed version, probably the one that he published. So the frequency of your spring is equal to and depends upon the mass of the objects on the spring and the spring's force constant. That just means the stiffness of the spring. So the larger the K, the stronger the spring, or the stronger the bond between the atoms. Yeah. So as K increases, the frequency increases. So as the strength of the bond increases, the frequency increases. Yeah. Frequency increases, that means we get a larger wave number. And we see this relationship. The spring stiffness of bonds increases in order of single bonds, double bonds, triple bonds. That makes sense. So the vibrational frequency increases, and it's higher for a triple bond than it is for a double, and higher than the double than a single. So then we take a look at the denominator. This value that's calculated from the two masses is called the reduced mass. And they've given it a symbol, the Greek letter mu. When one mass increases while the other remains the same, the reduced mass increases. So if we increase M1, say, M1 gets bigger in the numerator, but it's a multiplier up there. It's a product. It gets bigger by the same amount in the denominator, but there it's only a summation. So it doesn't affect the value as much. So overall, when you increase one of the masses, you're increasing the reduced mass. And as the denominator increases, right, it's in the denominator, as that value increases, the frequency must decrease. So if you increase the mass, you're decreasing the frequency. That's just an explanation of why it happens. Okay, now let's look at the intensities of the peaks. We've talked about the position of the peaks in a spectrum. Now, what affects their intensity, right? How big they are. Quantum mechanics tells us that a photon is more likely to be absorbed if a particular vibrational mode causes oscillations in the magnitude and orientation of the molecule's dipole. That is, stretch. These oscillations tend to be more pronounced for a stretching vibration when the bond is polar. So a stretching mode of a vibration involving a highly polar bond tends to have a stronger IR absorbance. That is, a carbonyl will give you a stronger signal. It's at a different wave number, but it'll still give you a stronger signal than an OH. And since we're talking now about polarity, the polarity between carbon and oxygen is lesser than it is between oxygen and hydrogen. So the highly polar bond, well, actually, we're not comparing those two. I'm sorry. The carbonyl and the OH bonds tend to be very large, very strong IR absorbers because of their polarity. Whereas the stretching mode of a nonpolar bond is very weak. It could even be non-existent if the two portions connected by the bond are similar. What they mean by that is this one, like that, versus this one. Let's see, 1, 2, 3, 4, 5. Yeah, let's do another one. Okay. So if you have a double bond on this end of the molecule, what you have out here is a methyl group versus the rest of the molecule. If we put the bond here, you have an ethyl group here and an ethyl group here. Well, actually, it's a propyl group on that double bond, but these are more similar to each other than this one is to that one. So the dissimilarity gives you a stronger peak. If they're very similar to one another, this peak might even disappear, even though it's there in the molecule. You may not be able to find that peak. So where we're headed with this is we're going to go back and calculate the index of hydrogen deficiency. And that tells us something about whether we've got cycles, double bonds, triple bonds, those types of things. And then you can use that information also to say, well, the index tells me that it's probably got a double bond in there somewhere, but I can't see it. So that tells you where to move the double bond in the molecule. Medium intensity absorptions will occur when you have dissimilar. So this one will be a medium absorbance, and this will be very weak or non-existent. And here are two examples. 1, 2, 3, 4, 5, 6, 7. I needed one more for mine. But the lesson is that with the alkene, the terminal alkene is going to give you a substantial peak, whereas the internal alkene is lost in the clutter, as they say. It's lost in the baseline noise. That's another thing that we tend to gloss over in general chemistry and even organic chemistry is teaching students about the importance of background noise, because every spectrum has background noise. And what you try to do is use a technique or an instrumentation that's good enough to differentiate true signals from background noise. Okay. Right, and that's what I just been saying. Okay, some important infrared stretches. That's an understatement. When you first encounter an IR spectrum of an unknown molecule, it may seem daunting. Even a simple compound can have dozens of peaks. That's true. So where do you begin? Well, when you look at the fingerprint region, you're going to have a mess. So we avoid the fingerprint region below 1400 and look at above 1400. That gives us a better starting place. So you want to learn to recognize certain spots in a spectrum that are unambiguous in their information. And one of those, the first ones we're going to look at are the hydroxyl stretches, the OH stretch. Okay. So this region above 1400 is usually not too crowded. And then when we need the fingerprint region, we look there for the presence or absence of specific peaks. And that, I call it tiebreakers. So here we have a cyclohexanol, and you see that broad peak, the OH, near what? About 3350 or 3325, something like that. That would be cyclohexanol. Let's see, I've got some comment here. Above 3000, yep, the OH stretch. Centered usually near 3300, and it's usually well separated from other peaks. When we get OH in combination with a carbonyl, like this butanoic acid, then the shape of the peak changes. This OH stretch, in fact, can extend down into the 2500 range. And that causes it to overlap a CH stretch region. So if you look for that difference, that appearance, then you likely have a carboxylic acid. Now here's why. The reason you have that modification and broadening of the peak for our OH in the direction that it goes is due to hydrogen bonding. Right? In the OH, you have hydrogen bonding, but it's not the same type of hydrogen bonding as you do with the carboxylic acid. All right, if you just have the OHs, you get the hydrogen bonding and that broadens the peak. But if you get a carboxylic acid, then you get, it looks like pairing of hydrogen bonds between molecules. Okay, the broadening of the OH peak is due to hydrogen bonding, yes. A network of hydrogen bonding facilitates a rapid exchange of hydrogen atoms from one OH group to another. Right. So you actually got some chemistry going on in there. See all those curved arrows. This process gives rise to a lot of variation in the OH bond strengths. Yep, it does that. So since we've got lots of variability in the OH bond strength, then its resonant frequency is going to be rather broad. It changes. It's got a lot of participants. When we got the OH stretch in a carboxylic acid, the frequency is generally lower, takes less energy. And frequency is lower. Because the carboxylic acid can form these dimers. More extensive hydrogen bonding than is normally found in alcohols. All right, what do we have here? Looks like an ether, 2,5-dimethyl tetrahydrofuran. I think the point of this slide is the nasty effects of impurities. Impurities can give you peaks that are not due to your molecule. So if you've got a preparation where you have water in it, right, you get an OH. You get lots of OH in that one. But maybe your molecule doesn't have OH in it, like this tetrahydrofuran. Right? That's essentially an ether, a cyclic ether, or a heterocyclic molecule. And it should not have OH in it. But we see just a slight amount up here at the top in the region where we would expect OH. It's probably due to impurities. Alcohols, if you use alcohol in your preparation, right, or in your synthesis, or water, these impurities can affect the spectrum. All right. But we can also eliminate that as impurity because typically if the molecule has an OH group in it, we're going to have a very strong absorption. Much more intense. So that emphasizes the fact that your method should include elimination of impurities too. So I guess we could do things like this hydrofuran, if it has a lower volatility than alcohol, we can get the alcohol out of it fairly easily. If it has a higher volatility than water, then we may want to sublimate it. Right? Cause it to vaporize out of the solution, leave the water behind, and then condense it on a cold finger. And the various cold fingers you use, depends. Cold water, ice water, You may even put dry ice in there to condense it. And that should remove most of the impurities. Okay, NH stretch. We've talked about the OH stretch. Now, how about the NH stretch? They share similarities with those of OH stretches because the oxygen and nitrogen are right next to each other in the periodic table. So they have similar masses, not exact same masses, but similar. And their polarities are not too different. And they are also, they can contribute to hydrogen bonding. So the NH stretch appears between 3,300 and 3,500. So it's a little bit higher in energy required. We get broad bands, right? We can see these broad bands simply because we also get hydrogen bonding with NH. There are noticeable differences between the OH and the NH bands because NH is slightly less polar. So we should see weaker hydrogen bonding. So the bands should not be as broad as the OH. The intensity also should be less because of polarity. All right. So here we go. The number of NH peaks can be used to distinguish between various types of amines. Right. We didn't do that with the OHs, but if we have a primary amine, then we should expect to get two separate peaks for NH stretching. Whether it's an amine or an amide, if it's primary, then you're going to get a double peak. If it's secondary, you're only going to get one peak. And I don't know if this is the cause, but for practical purposes, since that amine is primary, it has two hydrogens. So we're going to get two peaks. Secondary amine only has one hydrogen, and we should only get one peak. I'm not saying that's the reason. I'm just saying that's a trick. At or near 3,500. Okay. And then if we have a tertiary amine, we're not going to get a peak at all. Why? Because there are no hydrogens. All right. So this primary amine or amide can have two different modes of vibration. Right? We can get a symmetrical stretch or we can get an asymmetrical stretch. And this is probably the reason for the split. Because you can get a symmetric stretch at one wave number and an asymmetric stretch at the other wave number. That makes sense to me. How about the carbonyl group? It's found in lots of different classes of compounds. Ketones, aldehydes, carboxylic acids, amides, esters. It's all over the place. So usually the carbonyl stretch is strong, and the band is relatively narrow, which should make it easy to spot. And they occur, these stretches, the carbonyl stretches occur in this region between 1600 and 1800. And because the band is usually narrow, it's easier to differentiate among the different types of carbonyls, whether it's an ester, an aldehyde, ketone, whatever. Now, what happens when we conjugate it? Conjugation reduces the amount of energy required, so the wave number will decrease. If you conjugate a carbonyl with this alkene, right, like we've learned in the last chapter, If you conjugate those bonds, you're going to reduce lower the energy by about 20 to 40 wave numbers. So we went from 1721 to 1690. What's that? 30, 20. 31. The differences in these frequencies reflect the differences in stiffness of the carbon-oxygen bond. I don't know why that one's out there. That was a mistake. The stiffness of the carbon-oxygen, the carbonyl bond, increases in order of amide to ketone to aldehyde to ester. So ester is going to have the stiffest bond, aldehyde be the next, ketone be the next, and amide be the weakest of the bunch. So that should correspond to those list of frequencies. And then conjugation decreases the stiffness. So if amide should be the weaker of the bunch, it should have the least amount of energy required. So let's see if that's true. Let me go back. Amide. Yep. It has the smaller wave number. So that's explained by the stiffness of the bond, the strength of the bond. Okay. How about alkene stretches? We mentioned that earlier, didn't we? Yeah. The hep1-ene versus the tran-hep3-ene. The difference in the components that are on either side of the bond determine whether you have a strong absorbance or whether you have one at all. Right. Let's see. They typically occur in the range of 1620 to 1680 as a single peak. Now, what happens if you have, I'm just curious, what happens if you have one of these in here, but it's not conjugated? You have one over here, so, right here. If you have one over there, it's the same thing. If you have one here, then you should get, two peaks? You might get a broader peak. Yeah, but it would be more intense too, because you have dissimilar for both of them. Okay, an alkene stretch can sometimes be difficult to identify in our spectrum for two reasons. One is an alkene stretch can appear in the same region as some carbonyl stretches. That's true. Yep. In which case the absorption by the CC stretch can be obscured. Yep. Or second, in some highly symmetric alkenes, such as the bottom one, the CC stretch is very little absorbance. It just disappears. So you may have to infer alkenes by some other method. Maybe mass spectrometry would help there. Okay. How about CC stretch frequencies in aromatic molecules? Well, let's look at it this way. Since aromatic molecules are dislocated in terms of their electron density, then we should have identical bonds all around that are not quite as stiff as a double bond. So they should take less energy to make those stretch. And in fact, it does, 1460 to 1600. But there are also influences from other components. Let's see. In that top diagram, we have, I forgot to put the name in for that one. What is that? 1, 2, 3, 4. 2-phenylbutane. Yeah, 2-phenylbutane. And then the one on the bottom should be para. Let's see, for para. So tertiary butyl. Para ditertiary butyl. Benzene. Okay. Let's see. These three peaks are present for the top one, and they're relatively intense. Now, why are there three peaks? Well, let's see. Do we have three different types? We've got an attachment there. I would be willing to guess if this were benzene, that there should only be one peak, because all the bonds are equal all the way around. There's no influence from outside. But we should get a different stretch close to that 2-butyl subgroup. And then as we move away from it, we should get another one. And if we move farthest away from it, yeah. So this would give us one value, this would give us another value, and this would give us a third value. I think that's what's happening. For the we get only two peaks for the second one. So if we have a group here and we have a group here, right? So we have this one is the same as this one, and then this one is unique. So we only get two peaks for that one. That made sense to me. Okay, alkyne and nitrile stretches. They're going to be similar, simply because of the nature of the bonds. But the nitrile is a little more polar. Right? The alkyne is nonpolar, but the nitrile is slightly polar, so it's going to give us a different. It's going to require a little more energy, right? So it bumps up just a little bit in Wade number. One way to distinguish between the two functional groups is to search for an alkyne CH peak. Yeah, okay. Look at it this way. If you have an alkyne here, then you can have a hydrogen over there. Not always, but if it's a terminal one, you'll have it there. What about that one? All you have there is a lone pair. You don't have any hydrogen. Right, so you're not going to have an amine stretch of any kind. The presence of one appears that the sharp peak is consistent with the terminal alkyne. Yes. The absence of one may still leave us the choice between the nitrile and an internal alkyne, right? So then, if you don't have that, then you have to go to plan B. So if you do have the alkyne stretch with R groups on either side and not hydrogens, the bands are typically weak. Right, so if you have an internal alkyne, then the band's going to be weak. While the carbonyl has moderate intensities. Right, so they're going to be very close to each other. If you've got both of them in the same molecule, then you've got your work cut out for you. So how about carbon hydrogen? This is different carbon hydrogen stretches depending on their nearest neighbors. So the alkynes are going to occur about 3,300, right? So that's close to the hydroxyl stretch. So you can have a problem there. Alkenes are going to take a little bit less energy, and aromatics about the same as an alkene. Alkanes are going to take even less energy, and aldehydes are going to be less energy than that. But the aldehydes, looks like aldehydes are going to give you 2 peaks. Aldehydes. Why does it give you 2 peaks? Hydrogen bonding. It's difficult to interpret unambiguously. Okay, that's okay. Another understatement. So here we have an aldehyde, and it's very close to where you would find the hydroxyl, except this molecule doesn't have a hydroxyl in it. So my guess is that you would have to, I don't know, maybe the index of hydrogen deficiency would give us some information there. Maybe not, because oxygens have the same value as hydrogens when you're calculating that number. All right, so that wouldn't be a good approach. So if we get a stretch at 1720, carbonyl stretch at 1720, is there one there at 1720? Let's see, this is, yeah, about 1720, big one. Yeah, right there. It's either a ketone or an aldehyde. So then we go over to and look for the double peak at the aldehyde carbon hydrogen peak and find that double peak. Now we know what's an aldehyde, not a ketone. It's a detective story. Stretch intensities. All right. They're not very useful. Alkane carbon hydrogen stretches are not very useful because they're so common. They don't give us any identifiers. So we don't start there. Oh, I like that expression. I got this from the author's notes. It's like trying to identify a car from its tires.
Yeah.
Now, some exotic foreign cars, you can do that.
Yeah.
Because they won't run the kind of tires that you and I buy. I mean, their tires have to be good up to like 140 miles an hour or 200 miles an hour. Mine, they'll probably give out at 120.
I buy the cheapest ones from Walmart most of the time.
Yeah, well, that's one of the reasons I keep my Plus membership with Sam's, because it gets me a really nice discount on tires.
Really?
Yeah.
I didn't know that. I have to look into tires there now. I usually just get them at Walmart, and then my boyfriend he has the tire machine
Oh,
at
yeah.
home, so he puts them on the rims for me.
Okay, that saves you the installation fee.
Yeah.
Uh-huh. Yeah, well, your approach may work better.
Yeah.
And then you know who to blame if something goes wrong.
Yeah. Yeah.
Okay, so let's see, where are we going from here? These alkane carbon hydrogen stretches are most useful when they're low in intensity or absent altogether. Right? Then you can eliminate them as part of the structure. So the relative intensity of the alkane carbon hydrogen band decreases as the relative number of the carbon hydrogen bonds in the molecule decreases. And that makes sense. So the intensity is going to decrease as you decrease the number of those alkane carbon hydrogens. This 2-ethyl hexane 1-ol has 17 carbon hydrogen bonds. So you get a huge carbon hydrogen alkane stretch peak right there. Whereas with the ethanol, you've only got 5 carbon hydrogens. It's a much weaker stretch, less intense. And of course, they're both situated next to the OH bond. They both have the OH peak, so we know it's an alcohol. This other example where you have acetone, benzophenone, has no alkane carbon hydrogen bonds. Wow. We have to get down close to the, well, we get the carbon-carbon stretches down here where we see we're getting close to the fingerprint region, but we do get the carbonyl stretch. Is that it right there? I think that's the carbonyl stretch, that one peak right in the middle of the graph. All right. So this gives you a flow chart, right? Way approaches to identifying, and I'm not going to go through this because I'm not trying to turn you into a analytical chemist. And I'm not the person to teach that. I mean, I know some analytical chemistry, but it's inorganic. And let's see, I'll let that ride. So we're going to, the authors prepared slides for 3 different unknowns. I left them in here, but I only modified the one for unknown 1 so that we could just look at this one as an example. And then the second and third one, we're going to skip over. So here we have a C7H8O. 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 Okay, you remember how to do the index of hydrogen deficiency? I had to look it up because it'd been so long from first to 11. That's where we did that. You take the number of carbons and you can either multiply that and add 2. I like to add 1 and double it. You get the same answer. So that'd be 8 times 2 is 16, right? 16. Then you subtract. This would be the number of hydrogens. This would be the number of hydrogens in the fully saturated molecule. Like if we wrote C7, then how many hydrogens would you have? You'd have 16. That's a fully saturated alkane. So we're starting from there. And then we subtract the actual number of hydrogens we have. And we ignore the oxygens. Yeah, oxygens and sulfurs don't count. And then divide by 2. So that's 4, isn't it? 4. So we have 4. That means we could have deficiency means we could have 4 cycles. We could have 4 double bonds. We could have 4 cycles, 4 double bonds. We could have triples count as 2, so we could have 2 triples, or we could have any combination. Right. So let's see. I think that's where this thing is heading. Right. We have that. We know that we've got an alcohol group. So that means one of those hydrogens is taken up in an OH. We know that's there based upon that first peak to the left. That seems to be the one that's easiest to recognize if it's there. So that means that oxygen, that we have that one oxygen, this is the molecular formula that we got up general chemistry. that oxygen is not a carbonyl. We should not see a CO stretch anywhere in that thing. And if we look for a band at 1700, all right, 1700, It's not there. No intense band at 1700. So that confirms that we have an alcohol. Then here's the index of hydrogen deficiency. And all right, we don't have any nitrogen, so we don't add. If we had nitrogens, we'd add 1 hydrogen and 1 carbon to the calculation. But since we don't, we end up with IHD. HD equals. This is 8 divided by 2 is 4. Okay, what does that mean? We could have 4 rings, 4 double bonds, or 2 triple bonds. Right, got that on the board already. And it could be other combinations. So since we have relatively few carbons in this arrangement, you know, it would take, if we have 4 double bonds, say, one, two, three, 1, 2, 3, 4 double bonds, right? Then we only have what? 2 more carbons left over. That would be hard to make because these will have no hydrogens on them. Like these 3 right here. All right, so that's not enough room for the hydrogens. Our best bet is to go to rings. Introduce a ring in here. And if we do, introduce an aromatic ring, that would look, remember benzene is C6H6. Right? So I see similarities there. We take away one of those hydrogens, now we got C7H7. So we could have an aromatic ring. Right? And that would use up one of these. Just the ring structure itself would use up 1 ring. Okay. And then we would count 3 double bonds. 3 double bonds, and that uses everything up. Because you count the rings and the bonds separately. Right? So we've used up our IHD here with 1 benzene ring, and that gives us 6 carbons and 6 hydrogens. Now we have an oxygen, so we have to attach an oxygen here with its hydrogen, and that gives us makes 7 hydrogens. Let's see, we have 1, 2, 3, 4, 5, 6. We have 2 more hydrogens that we need. Okay, aromatic. Okay, there's more. Excuse me. So, do we have an aromatic? OH centered 3300. Let's see, an alkene or aromatic at 3050. 3050. Yep, there it is. Okay.
With the rings on it.
CH stretches 28,000. CC stretches at 1450. And yep, so we got those. And then step 2. CC stretches, but there must be more to this. Okay. All right, we have a bunch of choices. All right, we're kind of stuck at this point. So the CH peaks are present, but they're kind of low in intensity, much less than the alcohol band. Relatively few alkanes, right? And that's consistent with an aromatic. So, and we don't have a carbonyl, so we can skip that. And these are possibilities. Right. So you could have, let's see, if we had this one, actually we can't put that directly on the molecule because we need another carbon. So if we put, if we had a benzyl carbon and then an OH, then this would have 2 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. Yeah, that one would work. But we've got some others that would be just as valid. And this is where we're stuck. These are proposed formulas. And we went from this one to this one, where we had a phenol, but then we had to account for the other carbon. Right, so we could put the carbon there, right? Ortho, we could put it meta, or we could put it para. And that would account for all the carbons, hydrogens, and the oxygen. Okay, this just demonstrates one of the limitations of IR spectroscopy. Right? You can get so far, and then you need help to go farther.
Like from what?
You could use well, so far we've covered mass spectrometry. You could run it through your mass spec, and the fragmentation pattern would probably be different. So it would definitely be different between this one and any one of these, because the fragmentation would probably occur here. It's unlikely that you would break up that phenyl group. And we could, at least with mass spec, we could separate G from HIJ. And if we found the pattern was agreeable with G, then our problem solved. If not, then we got to go further. And we could use other techniques. I don't think UV vis would help much, because it doesn't speak to structure. You might have to look at different boiling points. Right, those isomers might boil at different points. Well, let's see. That's melting points. Those are going to be solids. Right, I got a bottle of phenol in the back over here. It's solid. Right, phenol is solid. So the methyl phenol is obviously it's going to be solid too. So melting point might give us a clue. Try to keep it simple. I mean, if you have high-powered instrumentation, then you can always fall back on it, but the simpler the better. So if we can differentiate with melting point, in fact, when you isolate a compound, that's one of the first things you do. If it comes out solid, you're going to put it in your machine and get the melting point. That's typical. If it's a liquid, you're going to stick it in a pycnometer and get the density. That's a little, looks like a volumetric flask, only it's designed so that when you put the liquid in there and you put the lid in it and no air bubbles are left, and then clean up the outside, then you know inside you have exactly, I don't know, 1 mil, 2 mils, 3 mils, and then you get the density from it very accurately. And other various things that you could do. Refractive index, right? They might have a different refractive index, depending on whether they're well, they are isomers of each other, so you should get differences there. Okay. All right, I've already told you about those. All right, here's the unknown 2. There's the possibilities for unknown 2, right? We have a carbonyl band, we have an alkene stretch, and then we have the alkanes for that one. And then this one, C8H14O, let's see. Oh, this is the solution for number 2. Number 3, we should find All right, it didn't go into as much detail. Here we have a nitrile stretch. And that's why we have this terminal nitrile here. All right. CH bending modes vibration for 2. Didn't we already do this? We see that earlier?
Yeah.
Table 16.2. Maybe there's something we want to say about it. No, that must be a duplicate. Sorry. Patterns for bending vibration. Bending vibrations are going to occur in the fingerprint region. So, and they're going to be a little more difficult to tease out useful information. For a monosubstituted benzene, you should get a split peak. But for this para-disubstituted, oh, those are the molecules we were looking at before, weren't they? So that's why you get a split peak with the monosubstituted. And the para-disubstituted is, why don't we get a split peak there? 1,4-ditertiary butylbenzene. I'm sorry. We're looking at bending. Now we're not looking at stretching anymore. Sorry, we're looking at bending. Right. So if we're bending a monosubstituted, it looks like we have 2 types of bends. We can bend this way or we can bend out of plane. So I think that's why we get 2 peaks. With the para-disubstituted, the bending there is going to be limited, probably to out of plane. Because if we try to bend in plane, we're going to bump into something. So we only get 1 peak for the para-disubstituted bending vibrations. Okay. Well, I don't know if that helps a lot. Bending absorptions can be particularly valuable when multiple structures are considered with the stretching absorptions. Okay. That's just a blanket statement. Sometimes we can use bending absorptions to differentiate among the various. Well, in our last 3 examples, where we had those possibilities of the ortho, meta, and para, maybe they give us a different bending peak. We didn't think to look there. Okay, that's enough for IR. So let's take a look now at ultraviolet visible. You can get the same output for ultraviolet and visible spectra. Only we're not interested in percent transmittance. So when we get the intensity of the detected intensity versus the source intensity, that would give us a value, but the problem is related to how we use the information, right? This is for concentrations. As concentrations change, if the concentration of your molecule change, then this will change also. And we're going to look at that in a minute. It's Beer's law. You've been introduced to that one already, I'm sure.
Yeah. What was it? The second lab?
Yeah, I think
We
so.
talked about it. Yeah.
So since this is a nonlinear response to concentration, and ultraviolet and visible spectroscopy gives us information about quantities. We use it quantitatively primarily. You can get some structural information, but it's not particularly useful, because in the visible and the ultraviolet range, you're dealing with electron transitions. You're not dealing with structural movements. So what we do is we take the log of this. And since this is going to be a negative number, the log is going to be negative, so we want to make it positive. So the negative log of this would be pi. No, I'm just joking. Like pH.
Yeah.
Negative log of this is going to be the absorbance. A, or absorbance. Absorbance. Absorbance is a linear response to concentration. That's what we want over a certain range. If you get very low or very high, then you sort of lose it. But we're shining a particular wavelength of light through the sample, and we have to use a dispersing device, either a prism, or more commonly now we use gratings. You'll get that in physics when you study light. Gratings will, in fact, gratings are better because they work by reflection mostly. You can get transmission gratings, but now it's usually by reflection, and that way you can get a more efficient transmission of intensity from your source with a grating. In fact, gratings are probably easier to manufacture. In fact, the first spectrometer that I used, plasma spectrometer that I used at the USDA, used grating, but they did it mechanically. They took a piece of glass and they scratched it to make the grating, and then they made replicas of it. And making replicas minimizes the flaws that are in the original. But then the second one I got was made with a holographic technique, and it produced a large grating and on the surface of a mirror. So they got focusing and spectrum at the same time from that mirrored surface. But you pick out a wavelength, and if you have to, then you'll just rotate the grating. So you scan through the spectra till you find the one you want. And then you shine that one through a slit that eliminates any stray light from the others, and then through your sample and then the detector. And you compare the source intensity to the detected intensity. And the graph is different. Absorbance is a measure of how much light is absorbed by the material, whereas transmittance is how much light is transmitted. So for the IR, we get something like this. For the visible and the ultraviolet, we get something like this. Goes the other way. Simply because this is how much light goes through, this is how much light is absorbed. So we have absorbance on the well, we've got a picture of it here. Absorbance is on the y-axis and the wavelength is on the x-axis. If you're going to produce a spectrum for your sample, then you'll scan through wavelengths. And modern UV vis spectrometers scan very fast, right? It takes less than a minute to do a complete through the visible and the ultraviolet, you get the whole thing. For this sometimes you get very, very simple spectra. For a buta-1,3-diene, you get just a single peak. Now, anything from 200 up to, what was it, 740 or 720, 740, I think. From 380 to 720, maybe it was, is visible. Below 380 down to about 200 is what's called I don't think it has a name. Let's call it air UV. In other words, you don't have to remove the air from your sample because it doesn't absorb in those wavelengths from 200 to 380. 380. Less than 200 nanometers. This is called vacuum UV because light will absorb that. Air will absorb that light less than 200. So if you want to work in this region, you either need to evacuate the light path, or you need to flush it with a gas that will not absorb in that region. And that usually works with nitrogen. Nitrogen won't absorb in there. The culprit in air that absorbs in that region is oxygen. So what we're showing here is everything above 200. My plasma spectrometer, we were able to run down to about 120 because we had the whole system flushed with nitrogen. And the nice thing about that is it also flushes out. It keeps a positive pressure on the inside. It keeps contaminants out. The previous spectrometer I had was ran on a vacuum. So it evacuated the chamber, and you get oil streaming going back. Even though you're pulling out, you still get oil siphoning streaming into your spectrometer and coat your optics, and it's a mess after several years. So the flushing method is best. I mean, and if you want to go down further, you may have to pick a different gas, maybe helium flushing. Or argon. Argon might work. And we used argon in the plasma. So it's available. I don't know. I never thought about that before. I know we use nitrogen because it's dirt cheap. Argon's more expensive. Helium is ridiculous now because it's very rare. In fact, we used to consider it a strategic resource, and the government limited it. We couldn't export it.
So I'm assuming like the helium for balloons is something mixed and it's not actually helium.
No, it's helium. Yeah, it's just that you use so little of it that it's economic. But if you have to use a lot of it, like for superconducting research, or well, for hospitals that have MRIs, they have to cool with helium, liquid helium. Some of them, I think, now will operate with liquid nitrogen, but it all depends on where your magnets become superconducting. If they become superconducting at higher temperatures, then you can get away with liquid nitrogen, which is a lot cheaper. But the main source of helium is not from the air. Well, the main source would be the sun if we could get to it. There's plenty of it there.
Yeah.
There's a lot of it on the moon too. But on Earth, the main source of helium is from natural gas. It's collected in natural gas at a much higher concentration than in the air. So when you purify your natural gas before you send it out to the consumers, you extract moisture from it, and you extract other contaminants, and you also condense out the helium because it's a valuable product. Now, we still have strategic helium reserves in Gulf Coast states that still have evacuated salt domes. That's usually where they put it. Either oil wells that have been depleted, or salt domes are better because you go down, you flush out a salt dome with hot water, bring out the brine, and it leaves this big cavern underneath the ground. And that's a perfect place. It's sealed, and it's a perfect place to store your helium. That's where we used to do, beginning with World War I, when helium was used in blimps and dirigibles. We didn't want to give it to Germany because they had the most advanced dirigibles in the world, and they were using them to bomb England during World War I. So we said, you can't have our helium. That's why they had to use hydrogen. And then the Hindenburg came over here and blew up, burned up because of the hydrogen.
Yeah.
Okay. Let's see. So we have this absorbance peak at 217 nanometers. And notice that the unit of measure here is preferred unit is nanometers rather than meters, usually listed that way. And then the relative absorbance is, relative absorbance means that it's been attenuated to a 1. Right, so the peak has been shrunk. The actual value of absorbance is not used here. This is relative absorbance. So absorbance measured at different wavelengths is then attenuated to the tallest peak, kind of like our base peak in mass spec. But I've seen it other ways. I've seen it where the absolute absorbance is given. But this is probably the way reference manuals do it, because the relative height of the peak is all you're interested in, and the position. Where is it in the spectrum? The only time you would want absolute values for absorbance is if you were using it to quantify concentrations. Okay, so we get this table 16.3 is the longest wavelength. So you say you get a spectrum with wavelength. You get a spectrum that goes like this, this, something like that. You want to use the peak that is the strongest absorber. This one right here, the primary absorbance peak, if you want to do concentrations, because it's the farthest away from the background noise. That gives you the best opportunity to quantify amounts, to use concentration. So that's a true statement. The energy of the UV visible photon is taken up by one of the molecule's electrons. So we're looking now at absorbance of UV invisible energy is an electron transition. And in the molecules, that means molecular orbitals. We're not talking about atomic orbitals now. I mean, if you look at fireworks, yeah, you're talking about atomic transitions. Those are individual elements that are being heated up there and giving off their characteristic light. But for molecules, we have to look at molecular orbitals. So we're looking at the lowest, highest, the HOMO, the highest occupied molecular orbital, and then the next one up, the lowest unoccupied molecular orbital. What's the transition between those two? Okay, molecules that contain only sigma bonds do not absorb in the ultraviolet or visible regions. Their longest wavelengths are too short. So that means they're going to be down, like if this is 200, they're going to be way down here at, say, 70. But you're approaching X-rays now. Or that netherworld between UV and X-rays. Because this is, the electromagnetic spectrum is on a continuum. I mean, we subdivide it into groups because it helps us organize our thoughts and correlate with observed phenomena. But as far as nature is concerned, it's just one continuous band. Molecules that contain at least one pi bond have their longest wavelength greater than 160. Right? So they may still be in the vacuum UV, but they're approaching um, air UV. Conjugation. Conjugation of double bonds, right, where you have alternating double and single bonds. The more conjugated you have, the longer the wavelength. It will shift the maximum absorbance to higher and higher wavelengths as you increase the number of conjugated bonds. Right. So we're going to show you several of them in here. Beta carotene is a good example. Also, all other things being equal between two molecules, the species that has a lone pair of electrons will have a longer wavelength, longer maximum lambda. And we're going to show you using molecular orbitals why that is. All right, so what's the question here? Rank these species in order of maximum wavelength for their longest absorbance. Okay, the authors give us an explanation, but I think we ought to just say STUV. STUV. Okay, what are the differences? Well, U has no double bonds. Right? It's going to be the shortest. Right? It's going to be even out of the UV. So U should be the shortest wavelength, like that. The wavelength here, shortest wavelength is U. The longest wavelength should be one where we have conjugated double bonds. So V should be the longest, correct? Longest wavelength. Okay. S and V have lone pairs on those nitrogens, right? In order to make an octet, they have to have a lone pair on those nitrogens. So the difference between S and V is that V is conjugated and S is not. So S is going to be there. Well, that leaves T, doesn't it? T only has one double bond. So it's going to be in the vacuum ultraviolet region. Now let's see if I got them right. There's your logic. UTSV. Yep. That was pretty easy. Since it's fresh in our minds. Give me a few hours and I'll probably forget.
Yeah.
Okay. What about color? Now we're talking about the visible range. Well, let's go back to basics. White light is not white. White light is a mixture of colors. At least all the primary colors. Right? What is it? Primary colors: red,
Blue, yellow,
red, blue, yellow, red,
Yeah.
blue, green,
yellow.
red, blue, yellow.
Yeah,
Okay.
because blue and yellow make green.
Yeah, that's right. And red and blue make purple.
Purple, and then red and yellow make orange.
Okay.
Yeah.
Well, we need to be a little more specific than that. Since white light is coming from the sun, say, is every possible wavelength. All the colors are jumbled together between 400 and 700 nanometers. So when a compound absorbs a particular visible wavelength, you don't see that color anymore. You see what's left over. Okay. So for this compound in that beaker, that flask is formaldehyde. It absorbs in the ultraviolet region. It doesn't absorb any of the visible colors. So it has no effect on the white light. That's why whatever we shine on that formaldehyde is the color we see. Okay. But for carrots, they have this beta carotene, which is we perceive as orange, but that's not the wavelength that's absorbed. it's the complementary wavelength to orange that's absorbed. Right? So that's why I gave you that very last pie chart. Complementary colors, there you go. So if we see orange, then it must absorb in the blue.
Oh.
Yeah, if we see let's see, if we see green, then it must absorb in the red, or if we see red, it absorbs in the green.
Like purple, you know.
Right. So if we see green leaves, they must absorb in the red. And they also absorb in the blue as well. So the red and the blue, so we get these combinations of green.
So like when you're colorblind, you can't see.
That's physiology again. You have defective cone cells.
Yeah.
Now, I've only got slight color blindness. It's not serious. But I noticed, especially when I first started driving, I say, why does everybody say you have to, when the light turns green, you can go? It's when the light turns blue, because that's the color I saw.
Yeah.
Okay, so if we get a maximum absorbance at 455, that's in the blue range. Right? If we go from 400 to 700, this is red, this is blue. Well, blue is here, and this is indigo violets down here. That's Roy G. Biv. But we see the color that's not absorbed. Well, and they're your complementary colors. All right. Here's the Beer-Lambert law. We're going to use this a little more rigorously than we did in general chemistry. So Beer-Lambert law says the absorbance of any pure compound is related to its molar absorptivity. And it's also proportional to the intensity. Here we go. No, that's not an I, that's an L. Excuse me. I should know that. That's L. Path length. How long is the path? So if the path gets longer, there's more absorbance, right? Because the light encounters more molecules. And then concentration. If we keep the path length the same, but we increase the number of molecules per milliliter, then we're going to get more absorbance. So these three factors are involved in the calculation of absorbance. Or what does the absorbance originate? Let's see. So in a quantitative experiment using ultraviolet or visible radiation, the path length will usually be held constant. And in our example in the lab, our path length, remember what our path length was? 1 centimeter. In those little square cuvettes, that's a 1 centimeter path length. And then the molar absorptivity is be constant for the molecule. We were looking for, that was kinetics. We were watching the absorption go down as the bleach took out our blue dye. And then, but if we wanted, and measuring concentration, which was part of our kinetics rate law, was proportional to absorbance. So we used absorbance rather than the concentration as a factor for the blue dye. Right? Remember, we had rate equals our constant times, let's see, blue dye, blue number 1, wasn't it?
Yeah.
To N, and then hypochlorite to the M. And we used absorbance for this one. We actually calculated molar concentration for that, but we used absorbance for the other one. Okay, Let's see. What's the point of this slide? I think I've got comments here. Yeah, it's most often used to quantify amounts of compounds. Follows the Beer's law. Kinetics measures absorbance versus time. Oh, I see where we're going with this one. We've got a synthesis here where we're taking this compound and let's see, put it over here. This is going to go through an elimination step using what is that? Methoxy group. So if we were doing the synthesis, we'd write it that way. But if we're going to do the mechanism, we would use that because the sodium is a spectator. And what we notice is that over time, we get an increase, and we're measuring the amount of this as a product at 244 nanometers. So that's why it's increasing. And it increases to a point, and then it starts to fall off. Why? Because we're using up our reactant to make the product. So we're not making as much. Okay, so what we want to do in this case is determine, we know it's an elimination reaction, excuse me. Got my double bond. We know it's an elimination reaction, right? Without that double bond, it wouldn't be absorbing there. So we're going to eliminate the chloride and leave a double bond behind. And we want to know, is it an E2 or an E1? Remember, E1s produce the carbocation first. So the elimination of this here is, right, that goes off as, and leaves behind the carbocation. That will be the E1, which means that we can change this concentration all we want, and it won't change the rate. Because the rate is dependent on the slow step. But if we change that value there, this is a, well, it's dependent on, it's a bimolecular, E2, bimolecular. So the attack of this one on that carbon causes the elimination. And the rate will change if we change that amount. Right? So we can look at this as a measure of the rate, and we find out, all right, what happens if we change the concentration of the base, right? If the concentration of the base is doubled, then we should see a doubling of the rate, right? Well, oops, sorry. We did it, right? And we did not see a doubling of the rate. Oh, wait a minute. We did see a doubling of the rate, right? So if we saw the doubling of the rate, that means this mechanism is E2. Okay, now for a deeper look at molecular orbital theory and ultraviolet spectroscopy. All right, here's where we have occupied molecular orbitals and unoccupied molecular orbitals, and the jump between the HOMO and the LUMO is the transition that's required to give us the longest wavelength. Actually, the longest wavelength, it could be any one of those jumps. The longest wavelength corresponds to a transition of electron from the highest occupied to the lowest unoccupied, called the HOMO-LUMO transition. Oh, yes, yes. Okay, okay. I'm sorry. The shortest energy jump gives us the longest wavelength. So the longest wavelength would be the lowest energy jump would be from the highest occupied to the lowest unoccupied. Those are the two closest together. Yeah. So if you look at those little blue arrows, the farthest one to the left is the shortest jump. Now you can get jumps from lower occupied to higher unoccupied, and that will give you shorter wavelengths. But the longest wavelength is going to occur between the HOMO and the LUMO. Now, what effect does conjugation have? Well, when we conjugate bonds, when the bonds are all sigma, there's a huge gap between the HOMO and the LUMO. Right? So that's why it takes a lot of energy, and the wavelength of the photon is way, way down, even out of the UV into the X-ray maybe. But if we just put one double bond in there, that decreases the energy gap between the HOMO and the LUMO. And if we conjugate them, then our molecular orbital structure brings all the levels closer together. It's like when we were talking about metals. Why are metals so conductive? Because the difference between the HOMO and the LUMO is almost nothing. Because you got all those atoms that are contributing to the molecular orbital structure, and the more you have, the closer the bands get together. So that's what's happening here. The more you conjugate it, the closer the HOMO and the LUMO get. And that requires less energy, longer wavelengths, to where you actually move into the visible region. Okay, and that's what these comments on the right are talking about. And I'll leave them up there long enough to get recorded. Okay. How about non-bonding electrons and HOMO-LUMO transitions? So when we were looking at non-bonding electrons, where do they go in the molecular orbital structure? Well, they essentially are not part of the bonding structure. I mean, they have to go into the molecular orbital structure for sure, but their energies don't change. So the non-bonding electrons are at the same energy level as they were before the molecule was formed. And there are electrons there. Right? So they are the highest occupied molecular orbital. And since they are at the same energy level they were before, they're not at a lower energy level, then they're closer to the LUMOs than any of the other energy levels before. So that gives us a longer wavelength, lower energy photons than when you have these non-bonding electrons. Let's see, in terms of transition, okay. Called the N pi star transition. I guess N is stands for non-bonding. Okay.